is Intan Azina binti Jamaluddin. My matric number is CE2200. I am presenting my final year project. Let's begin with the project overview. The core focus here was to design an integrated differential drive robot that isn't just a remote control robot but a system capable of high-level perceptions and autonomous decision-making. To achieve this, I utilized the robot operating system ROS2. This middleware is crucial because it bridges the gap between the low-level hardware control like spinning motors and the high-level algorithmic execution like figure out where to go. I used a Raspberry Pi for cognitive tasks such as mapping and vision processing. Other than that, I used an Arduino Nano for motor tasks ensuring precise speed control via PID loops. So why is this project necessary? I identified three main problems in the current robotic landscapes. First is the accessibility gap. High performance research robots often cost thousands of dollars, which limit access for students and small-scale developers like us. Second is algorithmic risk. Developing navigation software directly on physical hardware without a digital twin is dangerous. If the code fails, you risk expensive hardware damage due to collisions. Finally, there is a lack of integration. Most affordable hobbyist kits lack the computational power or the standardized software stack required to run modern AI and SLAM applications. My project aims to solve these issues. To address those problems, I established 5 key objectives. High fidelity simulation to architect a 3D environment in gazebo that mirror physical constraints, allowing for safe algorithm validations. The second one is autonomous localizations to implement LiDAR-based lab simultaneous localization and mapping for real-time environment reconstruction. The third one is intelligent navigation to deploy the navigation tool stack, enabling the robot to plan path and avoid obstacles dynamically. The fourth one is hardware architecture to develop a robust hardware config that integrates seamlessly with the ROS2 ecosystems. And lastly is modulator software to write modulator software nodes that handle communication protocols and data processing efficiency. To keep the project focused and achievable, I defined the following scope. For the software stack, I'm utilizing Ubuntu Linux running ROS2 Humble alongside the Gazebo Multi-Robot Simulator. The second one is for the hardware framework. The robot integrates an RP LiDAR E1 for 360-degree visions, a Raspberry Pi, and 12-volt DC motor equipped with Hall effect encoders for odometry, and lastly is operational boundary. The robot is designed specifically for indoor environments with flat terrains and is programmed to handle static and semi-dynamic obstacles. Now let's look at the software ecosystem that powers the robot. I employ a combination of industry standard tools. The first one is ROS2 Humble Workspace. This is the core framework managing all the communication. The second one is Gazebo, used for the simulation use. See in the top right, allowing me to test the physics and collisions. The third one is RVC, used for visualizations. This allows me to see what the robot sees, specifically the laser scan data and the map being built in the real time. The fourth one is SLAM Toolbox, used to generate the map, and lastly is Navigation Tool, the navigation stack that handles the path planning from point A to point B. Finally, this is the hardware implementation. The schematic which I designed in Cricut Designer, I illustrate the wiring logic. At the center top is the Raspberry Pi 4B, acting as the main computer. It receives power via a USB-C connections. It connects via USB to the Arduino Nano, and the Arduino Nano acts as a bridge reading the data from the motor encoders and sending PWM signal to the L298N motor driver. The RP LiDAR E1 connects directly to the Pi to feed high bandwidth laser data into the ROS2 network, and the entire system is powered by a 12-volt source tolerant to handle the load of the motor and the computing units. The architecture ensures a clear separation of duty between high-level processing and a low-level actuation. And lastly, I will show you my demo. The first one, start by defining your robot physical structure using a URDF file. This tells rows where the wheel, sensor, and the chassis are located. Then, before buying parts, you will set up a virtual version of the robot in the Gazebo simulator. This allows you to test your code and navigation logic without risking hardware damage. After that, for the differential drive controller, to configure auto control, I configure the ROS2 control package to translate move forward commands into specific wheel speeds. Next, I install the ROS2 Humble for my Ubuntu and on my Raspberry Pi. After that, I also install the LiDAR and ROS2 controllers and other codes for my mobile robot. Next, for the LiDAR integration, I install the drivers for my LiDAR, as RP LiDAR, and I'll figure out the scan data from the robot so I can see the walls. And lastly, for navigation and mapping, SLAM toolbox. I run the SLAM toolbox to drive the robot around and generate the map of my rooms. I also install the navigation tool stack to figure the navigation stack. This is the brain that allows us to click at a point on the map in RVs and have the robot plan a path to get there autonomously. That's all for me. Thank you for watching.